Good morning, everyone. I'd like to welcome you to the final installment in our 2026 Royal Tour Museum Speaker Series. Our work takes place through the provinces known as Alberta. We gratefully recognize and honor Indigenous peoples' longstanding connections to these lands. And I also want to take a moment to once again thank the Cooperating Society for supporting the Speaker Series this year. And as this is the last talk, I'd also like to give a general thank you to everyone who's been involved in facilitating this. So today we are happy to welcome John Acorn. John is an Alberta boy. He was born, raised, and still lives in Edmonton. And he has a longstanding interest in all aspects of natural history and paleontology. John did his undergrad and graduate work at the University of Alberta. And then he went on to do a lot of science educating. He's written a number of field guide books. He developed 2 television shows back in the day of appointment TV, Acorn the Nature Nut and Twits and Pishers. And he has a relationship with the Tyrrell Museum. He did a series on CKUA called Deep Alberta, talking about paleontology, and also developed and recorded some videos back in the day for the gallery. And today we're happy to have John sort of combine a couple of his passions, insects and the fossil record. So John will be talking about insects from central Alberta and the story of life after the dinosaurs. So John, we're looking forward to an FAB talk. Only John will get that joke. Don't expect anyone else to. Okay.
All right. Thank you. Well, yeah, first of all, let me just say I'm really pleased to be here and thank you for the invitation. I do have such a long and fond association with the museum. So it's great to be back in this room and to see a lot of familiar faces and to see a good sized audience for such a wintry day as well. So yes, I want to talk to you about insect fossils from central Alberta. And, you know, I get the fact that insects, they're not dinosaurs. It's a little bit of a hard sell, but I'm going to try to make this as interesting to you as it is to me. So let's start with central Alberta, because the fossils that I'm going to talk about, they come from the rocks that we call the Pascapoo Formation. So these rocks date from the time after the extinction at the end of the Cretaceous, the extinction that killed the dinosaurs and so on. And there's a lot of Pascapoo Formation rock in Alberta. It was first named and described by you-know-who, Joseph Burr Terrell, 1887, and he described this rock formation from the area where the Blind Man River meets the Red Deer River near the town of Black Falls. The Blind Man, by the way, is a translation of the Cree word Pascapoo, which basically means they are blind, and it refers to a story of a hunting party about this time of year who were overtaken by snow blindness after a big, snowstorm, and it was sunny the next day and they all couldn't see, and that's a pretty bad thing to happen back in the day. So here we are at the junction of those 2 rivers, and Terrell noticed at the time that some of these rocks had really beautiful plant fossils in them, nice leaves and so on, and those were studied by a guy named Bell. And we're going to skip ahead now to the 1970s, and there was a botany student at the University of Alberta, Dale Spears, and his professor, Wilson Stewart, who was a paleobotanist, he said, "Dale, you're from Red Deer. Have you ever gone to these sites where the plant fossils come from?" And Dale said, "No, I gotta go check this out." So, oh, pardon me, I'm pressing the button by accident. So Dale got his mom to give him a ride, his mom, Betty Spears. And the long and short of it is, Betty became absolutely obsessed with the fossils of that part of the province, and she collected countless beautiful plant fossils. This museum has a huge collection of Betty Spears fossils. We have another huge collection at the University of Alberta in Edmonton, and Betty is really one of the major figures in fossil collecting in the history of Alberta, without any doubt, if you just look at the number of specimens that she collected. Somewhere in there, though, on the right is Dennis Whiten. He was an administrator at the University of Alberta, but his hobby was paleontology. He became interested. His partner, Patricia Mitchell, who was a grad student at the time, she wound up being a water quality specialist for the province. If you had a nice drink of water from the tap this morning, you'd probably thank Patricia for the quality of the drinking water. And they noticed that in among these plant fossils, there were also the occasional insects. And so there on the screen, you've got an insect larva. And so they became very interested in the insects as well as the plants. All of this was happening with the cooperation of a professor, Mark Wilson. And some of you will know Mark Wilson. He's now a retired professor at the U of A. Mark, early in his career, he was very interested in the insects, but then he decided, oh no, fish are where I'm going in life. So he became more of a fish paleontology specialist. But in the interim, he collected all of those insect specimens that Betty Spears had accumulated, and the Dennis Whiten specimens. They all came together in a big collection, which basically has been sitting there without a lot of scientific activity for, I don't know, maybe 30, 35 years. And now it sits in one corner of the Entomological Museum. And the person sitting with it here is Kano Sasiguchi, who some of you will know because she worked for the Terrell Museum for the last couple of summers. And Kano's story is that, her story in a nutshell, she's important to this story of the insects, is that she came here, 4 or 5 years ago, I guess 5 years ago, from Japan, from the middle of Tokyo. She's the most urban person that any of us knows. And somewhere in her childhood, she went to a museum and saw an exhibit about dinosaurs and Badlands, and something went ka-ching in the middle of her head, and she decided, I got to go there. So here she is. And then, and so she was, a kind of typical smart but dinosaur-obsessed person, which is fine. That's good. But then she took an entomology course from my colleague Felix Sperling, and something else went ka-ching in her head, and she realized, oh man, bugs are just as cool as dinosaurs. And Felix said, well, we have all these insect fossils. If you'd like to do something with them, you could do a study. And that was when she really sort of became an insect paleontologist, and I became interested in the study as well. Now, I'm going to tell you a little bit about my own story, just because I like telling my own story. And thankfully, Jim has already told you part of it. So yeah, I've got a nice long history with this museum. But before that, let me take you way back for me. When I was 5, my dad would take me to the library, the public library, and I would choose books based on how cool the covers were, because I couldn't read. And he would read them to me back home. And these were two of the books that changed my life. The How and Why Wonder Book of Insects, and at the time, 59 cents, and the How and Why Wonder Book of Dinosaurs, $1.25. What's that about? I don't know. And my whole life since then has been trying to balance the obsessions that developed from these two books. Paleontology on the one hand and the entomology on the other. I was lucky enough to get a job in 1979 as a park interpreter at Dinosaur Provincial Park. That's where I met my first, real paleontologists, and I was very inspired by paleontology. And the long and short of that is that I wound up starting a master's program with this fellow on the left. That's Dr. Richard C. Fox, who was primarily a mammal paleontologist at the U of A. I didn't finish that degree. The way I explain it to people is, he was old and stubborn, and I was young and stubborn. And he was really stubborn, and I was really stubborn. And so that didn't work out, but I still had a wonderful time, and I learned a lot about paleontology during that experience. Learned a lot about the Pascapoo Formation, because there we were back on those same rocks. I have a frown on my face in the upper picture because we'd been sitting on the same part of this muddy hill for like 2 weeks. 4 of us, we hadn't found anything. It was just like opening up one gray rock after another to find the inside of a gray rock. It's not a really interesting job. Andy Newman took this picture here. It's actually, it's kind of life-threatening work, really, sitting on the edge of that cliff in your lawn chair. I got in trouble with Dr. Fox for having a lawn chair. He thought that was way too cushy. I thought it was brilliant myself. And it wasn't easy to get the lawn chair into position on that cliff either. Anyway, the other thing that was wonderful about that experience was the other people I was working with, and one of them was Andy Newman. And of course, neither of us at the time knew that Andy was going to go on to become a director of this museum. And it's great that Andy's here today in the audience. It's super nice to catch up with Andy. Andy and I had wonderful conversations about absolutely everything while we're sitting there splitting the gray rocks, hoping beyond hope that we'll find a black fossil mammal tooth somewhere in there. That was my first year. This is another Paleocene site near Cochrane, by the way, if you're wondering where this picture was taken. And then the second summer that I worked for Dr. Fox, I spent a lot of time chatting with Dennis Walsh. Dennis Walsh was an undergrad and just one of the smartest, most curious people I've ever met. And the way Dennis tells the story, we were sitting there beside the banks of the Blind Man River, splitting rock, and we were finding fossil teeth. It was pretty good, paleontologically. And somehow the conversation, I mentioned the philosophy of biology. And Dennis said, "What do you mean the philosophy? What the heck is the philosophy of biology?" I said, "Oh yeah, there's a whole branch of philosophy that concerns itself with biology and how biologists think." And something in his head went pting. And his story from then on was he started a PhD in paleontology at McGill, then he switched to developmental biology, finished his PhD, then he went to Cambridge and got a doctorate in the philosophy of biology, and he's now a professor of the philosophy of biology at the University of Toronto. So it's amazing how these little tiny things, change lives. And this is Dennis's, the thing that he is best known for. He's got lots and lots of wonderful contributions, but a book called Organisms, Agency, and Evolution. The book is, I'll have to admit, it's one of my favorite books, but it's about as confusing at first glance as the cover. Dennis has the most incredible vocabulary of anyone I know, and he thinks about 300 times faster than any of us do. And so every sentence is just full of very carefully crafted meaning. So it took me months to read this book, but I still highly recommend it. As I'm getting ahead of myself. I'm just saying, isn't it wonderful that that the Blind Man River reminds me not just of ancient Alberta, but also of these big, broad, sweeping questions in paleontology and philosophy. Here's another book that I'm going to talk about philosophy for a little bit. I hope that's okay. Don't answer. This is another book that just came out in the last year about the philosophy of science, and I recommend this book. A philosopher named Michael Strevens, he calls it The Knowledge Machine, How Irrationality Created Modern Science. And what he means by that is that modern science works according to what he calls the iron rule of explanation, that every scientific idea should be judged by how it works with respect to the evidence, the testing with evidence. That's the only thing that matters to science. Leave the philosophy out, leave the religion out, leave the aesthetics out, just focus on the evidence. And he said, well, that's kind of irrational because obviously these other things do maybe kind of matter, but that's how science works. And I don't know, I think this book is going to make a pretty big splash in the small puddle that is the philosophy of science. But there's something interesting here. I mean, I'm convinced by his historical overview of the scientific process, but I can't help but wonder, what do you do? And I put the words on the screen so I wouldn't forget to say them. What do you do when philosophy sneaks into science as metaphor? When the scientists are making philosophical assumptions, but they don't know it because they're using metaphors and they assume that everyone knows what they're talking about and they're actually being literal. Let me give you an example. The example I want to give is the idea that the Paleocene time was a time of recovery. And I think everyone in paleontology has either heard this phrase or used this phrase. I'm guilty. I've said this. You know, there's this great whopping catastrophic event that happens at the end of the Cretaceous, and then in the Paleocene there's recovery. It's recovery after the extinction, after the asteroid impact, after this terrible, terrible event. So the question that one would ask if one was philosophically inclined is, what exactly does that mean? What does it mean for the Paleocene to be a time of recovery? What is it? What is the agent, to use Dennis Walsh's favorite term, that is capable of being injured and then recovering? Because it's obviously not the dinosaurs, the mosasaurs, the pterosaurs, the ammonites, because they're gone. They're extinct. They're not recovering. They're gone. It's something else that is recovering, right? That's the question. So and the broader question is, what is the story of life about? So, you know, I'm interested in not just doing paleontology, but communicating about paleontology. And of course, that's the function of this entire institution, is to communicate to the public about paleontology. And the question is, what is the subject matter of the story of life? Is it just regular animals and plants and, you know, funguses and stuff, things that we pretty well know existed for sure? Or is it something else? Is it the story of some broader concept? And when I say broader concept, think something away. Oh, well, John, it's not that the dinosaurs were recovering. It was that the ecosystem was recovering. Or the ecological communities, biodiversity was recovering. All of those are abstractions. You know, as soon as you start hearing this ecological language, then you're into abstractions, and some of those abstractions are what has been called superorganism concepts. That they're something. Like the whole ecosystem is like an organism. It's like an individual. It has its own health and it has its own troubles. And this idea has been very popular over the years, but it's also come under a lot of criticism over the years because it doesn't really hold together very well scientifically. It's a metaphor. Now, when I say it's a metaphor, you might be thinking, I don't know if it's a metaphor, John. That's maybe an overextension. But, you know, there's some metaphors that we recognize very easily. Mother Nature. This is, oh man, I should have brought my other picture of Mother Nature. I've got a picture of Mother Nature with you, Jody, in Southern Ontario. It's a different Mother Nature. This one is real. This is my friend Joanna. She used to dress up like this and go to schools and stuff. Lives in Palm Springs, California. We all know that Mother Nature is a metaphor, but how often do you hear scientists say, yes, Mother Nature was recovering during the Paleocene? I mean, that would be a normal sentence for someone to utter, right? I think it would. But we know that there's no Mother Nature. How come we are kind of a little bit confused about, by the way, it looks like Mother Nature bought my son a Coke and some corn chips there because natural stuff is good for you, right? So is it something else? Is it just, maybe it's just large animals that were recovering. Because we lost the dinosaurs. They were, not all of them, but most of them were pretty big. Mosasaurs were big. Maybe there's large animals that are recovering. And when you start thinking this way, I hope you're digging this. I love this stuff. Then you enter into this realm ecologically where you start thinking about niches. Pardon me, there's a picture of an empty niche. I photographed it on a trip to Victoria not long ago. And the idea is, and you've all heard this ecologically, that the environment creates this place, this role, this ecological role, and then the lineages that are evolving, they have to find these niches on the adaptive landscape. And it's all metaphorical, and it all sounds very sciencey, but it's all metaphorical. And once they find them, then the niches are occupied, and there's an occupied niche. And that these niches were made empty by the extinction, and then these other things found them and reoccupied them. And this is the way that ecologists typically speak. And this is also something that is coming under tremendous scrutiny from a lot of philosophers of biology, including my pal Dennis Walsh at the U of T. He's very critical of this notion of niches created by the environment, and then the animals have to find them. Here's a nice quote from Richard Lewontin. He was a wonderful evolutionary biologist at Harvard. This whole idea applies the autonomous existence of environments independent of living creatures. I was lucky enough to photograph a whole array of niches as well, all empty, all created by the environment. It's like the environment, the non-living environment, has some sort of plan for what the animals and plants will do, and they have to find the spots in the plan. And that's just, when you think about it, it's a weird idea. Are you with me? It's a little bit of so maybe there's another way to frame it. Maybe there's another way to sort of think your way around this. Here's another quote from Lewontin. The price of metaphor is eternal vigilance. Because metaphors are sneaking into science all the time. Some people say that we just can't work without metaphors. Metaphors are central to cognition. That metaphors on the one hand and categories on the other, those are the two things that make minds work, or at least human minds. There are linguists, George Lakoff, Mark Johnson, who have published remarkable arguments. And again, I think this is just absolutely wonderful, necessary reading for everybody in science. The notion that metaphors are not just figures of speech. They're not just something left over from English class. Metaphors shape our thought and they constrain our thought. And they talk about conceptual metaphor. And so this recovery notion, the Paleocene is recovery. That's a conceptual metaphor. It's not just a choice of words and you actually know what you're thinking even, independent of those words. Those words shape how we think about the subject. Okay, so I'm going to get less philosophical here and talk about the actual thing that's happening. So here's a nice little graph with pictures, so I like it, from a paper recently published in New Phytologist. And it's complicated, but right here, this little line that runs up to the red text, that's the extinction event. And everything to the right is what's happened since the extinction event. And you'll notice that all those spindles, so to speak, they all get wider. There's nothing that gets smaller at the extinction event in this diagram. Most of that is insects. It's not all insects, but most of it's insects. So it's kind of like, from the insect perspective, where's this recovery thing that we're kind of expecting according to the metaphor? And of course, there were groups of insects that existed during the time of the dinosaurs, the Mesozoic, that we don't see in the Paleocene. And I got to brag about this one because it was such a nice gesture. This is a whole new family of dragonflies that was described from a fossil found in Dinosaur Provincial Park a couple of summers ago and named in my honor by Andre Mueller, a grad student at McGill. So as far as we know, those things didn't survive into the Paleocene. There's a couple of cockroach families that didn't survive. There's a family of aphids that didn't survive, and so on and so forth. But for the most part, the bugs seem to have done pretty well across that magic line between the Cretaceous and the Paleogene. It's kind of a green dotted line here. All those graphs are going up. It's all up. There's no down and then up. There's no, like, recovery is down and then up, right? Like, I had this terrible, you probably had it too, this terrible virus that's going around. Last 2 weeks of my life, I was just like, ugh. I'm amazed I haven't had a coughing fit during this talk yet. I know what this feels like, this recovery thing. You go down and then you come up. None of these graphs go down. I mean, we could find other papers where graphs go down, but these are two very prominent. This is Nature Communications. This is a good journal. The graphs don't go down. So there's something missing in this metaphor. Okay, I said I was going to not talk about philosophy anymore, but I was lying. I forgot. I think paleontologists should be especially happy with the idea of philosophy because part of the word paleontology is ontology. And ontology is a branch of philosophy. It's the branch of philosophy that deals with existence. What stuff exists or what stuff existed in the deep past in paleontology. And I just think that's maybe one of the most interesting aspects. So, and you're going, well, come on, like, what are you talking about? Well, again, we often use these abstract terms like species. You know, to what extent do species exist? To what extent are species kind of not something that exists? And if they exist, how do they exist? I don't know if you've ever had to struggle with this question, but it's a big question. There's like a lot of discussion of that. And one of my favorite books on species, written by this guy, John Wilkins. And when I came to this quote, I just stopped and I almost cried because I thought, oh man, he's right. He says, one point that is not often discussed is whether biology overall even has an ontology. Have biologists ever really thought about ontology, about what actually exists and what is just an abstraction that they imagine exists? That's kind of a profound criticism on his part, but I'm kind of with him on it as well. And that's why I'm saying, hey, paleontologists, this is a big opportunity because you've already got the word ontology in the name of your science. And it gets weirder. Here's a new theory that is becoming popular. It hasn't won people over completely yet, but this whole notion that in terms of the ontology of science, or biology, pardon me, maybe that ontology should be a process ontology, not an ontology of what things exist, but maybe the only things that exist are processes, are events. That it's all, and how could that possibly make any sense? Ignore all the text at the bottom. Just read the top part. A process ontology for biology. Here's one of the big proponents, John Dupre. And he says, functions are just fast processes and structures are relatively slow processes. I'm fascinated by this. And I don't know, again, I'm thinking if anybody is going to get this, it's going to be paleontologists because they're used to thinking in terms of deep time and long periods of time. And I don't know, I'm not going to try to explain it or defend it. I'm just saying, here's an idea. It's popping up, and maybe paleontologists are in a good position to think about it. Okay, back to the bugs, in case your brain's starting to hurt. So this is just a sample of pond gunk from a pond near Red Deer. And when we look at our fossils from the Pascapoo Formation, we think that this is kind of what we're looking at. A nice mix of plant leaves. Some of them are kind of partly decayed. Some of them obviously have some insect damage on them. There's a partial exoskeleton from a giant water bug larva. There's a disembodied wing from a crane fly. There's shed exoskeleton from a dragonfly nymph. There's a couple of snails here. That looks a lot like what we find, as mudstone impressions at this point. But the real trick with insect paleontology is knowing whether you're actually looking at an insect or not. And this is where it gets really tricky. So here's one from Edmonton, from the Danic bone beds, dinosaur age. And the people who found it, they said, "Oh man, that's got to be a bug wing." So they brought it to me and to a couple of other entomologists and said, "Is this a bug wing?" And we all looked at it and we said, "Nah, I don't think it's a bug wing." And then they took it to the paleobotany people and they said, "Is this a plant?" And they said, "Nah, I don't think this is a plant. It's probably a bug wing." And then we started looking at it again, and we thought, "Oh, well, maybe it's a caddisfly." I think that was Cano's idea, which was a really brilliant idea. And so we reinterpreted these veins, and we said, "Oh yeah, it's caddisfly." But you know what? I think that's total bunk. I don't think it's a caddisfly anymore. I think it's a fern. I think it's a fern. And this makes our job hard, because next week I might think it's the caddisfly again. I was telling Cano on the way down yesterday, I said, I think that thing's a fern. She said, "Oh, John, I thought you were on my side." I said, "Nah, it's okay. I might be back." He said, "Well, I hope you still think the thing from Genesee is not a fern." And it's a little bit of a blurry picture, but right in the center, that sort of dark rusty brown thing, we believe that is a cockroach forewing. And for a long time, our paleobotany friends at U of A were going, no, it's a fern, 100% fern. Hate to burst your bubble, it's a fern. Well, we sent it to a cockroach fossil specialist. Such people do exist, they get paid. And he said, "Yeah, that's a cockroach." And he sent us, a diagnosis of it and said it's probably a new species of cockroach, and this is really exciting. So, like I'm saying, it's not an easy job. Now, sometimes it's a lot easier than what I've just showed you. So this has been known for quite some time. The color illustration is a living crane fly, these things that look like gigantic mosquitoes. And you can see the fossil wing. There's two wings overlapping. Oh, we'll come back. And the wing still has the pigment. Look at that pigment pattern. It's right there. The preservation in some of these fossils is so good. If that was dinosaur skin, oh man, front page of the New York Times. For insect paleontologists, oh yeah, it's the color pattern. Okay, that's cool. Now, crane flies live here in Alberta today. So we can find a fossil in the rock that looks very similar to living crane flies right here around us. Now, we do find caddisflies. Maybe that other thing wasn't, but most of what we find are the cases. The case of this caddisfly, and you've probably seen this, where the caddisfly larva, not the adult, the thing that flies around and looks like a moth, the larva puts together a little case, usually tubular, sometimes a spiral, made from pieces of, in this case, snail shell or clam shell. And then it walks around protected by this little case. So we find all these caddis cases. And of course, there are lots and lots, huge diversity of caddisflies in Alberta today. Again, this is what Dennis Whiten and those folks, this is what they expected when they first started studying these fossils. They expected to find the ancestors of the insects that live in Alberta today. Here's another one. On the left is a ground beetle. And there's a fossil that, I don't know, I've looked in my other life as an entomologist, I've looked at tens of thousands of ground beetle specimens under the microscope. That to me is a ground beetle. You may not be convinced. All but one of those legs is actually a piece of plant stuff. But that's a ground beetle to me. And again, it's a perfectly normal looking fossil. Then, okay, isn't that a cool picture? I don't have time to explain what this picture is. This is from reflectance transformation imaging. It's the normals image. And a group of us are in the process of describing a new sort of horntail sawfly, based on this marvelous wing that's preserved in tremendous detail. And again, we've got lots of horntails here. The larvae burrow in wood. You may have encountered horntail larvae in firewood and so on. And then we get insects that are kind of related to the Alberta insects now, but not really. So here's an Alberta giant water bug, and they're big. That's one of the biggest insects in the province. And I know Darren Tanky found one hanging out the lights near the staff entrance here last summer. We have a fossil giant water bug, but it's smaller and it's clearly more closely related to giant water bugs that live like in the southern states and so on. So we're kind of related, but we're starting to see things that are more sort of Florida-ish relatives. Same with some of the dragonflies. Here's a beautiful, look at this wing. Oh my goodness, beautiful. And it's very clearly a part of a member of a group, the Gomphaceae, that again, you need to go to southern Ontario or down into the southeastern states to find living Gomphaceans. So we're, and that's familiar. If you're familiar with the whole sort of Cretaceous scene, you've got things like garfish and soft-shelled turtles living here in the Cretaceous that are now more sort of southeastern. And then there's this. Now here I get to brag about Cano again. Cano focused on this particular type of fossil for her undergraduate thesis, and this is a beetle larva. Now, how do we know it's a beetle? Well, it's got a head on the opposite end to me, on the right end, and it's got 3 little legs, and it doesn't have any of what we call prolegs, and it's got the right number of segments. Yeah, it's probably a beetle larva. Back in '79, Mitchell and Whiten, they classified the beetle larval fossils into a type A, which is kind of a grubby looking thing. Type B, that's the one that Cano's focusing on, and it's got that long sort of horn sticking out the back end. Cool. Then there's type C, it's got antennae. Oh, that makes it easy. That there's only one family of beetle larvae with antennae, the Noteridae, they're burrowing water beetles. They don't live here. They live further south. And then there's a final 4th type that they called click beetle-like. And we're still working on what that one actually is. Probably not an actual click beetle, but something related. Anyway, back to the type B. So the problem with identifying beetle larvae is that there's unbelievable numbers of beetles. I mean, there's unbelievable numbers of beetles to start with. Like today, there's probably 500,000 named species of beetles on this planet. You got to sort through a lot of beetles if you're trying to identify beetles. And who knows how many species have gone extinct between 60 million years ago and today. So many of them look exactly like this. Like this is a superworm. You can buy them at the pet store and feed them to your pet lizards or tarantulas or whatever, thing you have at home that likes to eat beetle larvae. Wouldn't it be nice if they had nicer features? Like here's a larva. This is a scarlet malachite beetle larva, photographed in our upstairs bathroom at home. They live in lots of houses. Nobody knows what they're doing there. They're not pests. But if that was a fossil, we could recognize it. But so many of them are just... So anyway, Cano did a wonderful job of thinking about possible larvae to compare it with, and she narrowed it down partly based on the form of the larva, partly based on the habitat, based on what we knew from the plants and the geology, the sedimentology, and so on. And she said, well, probably one of these 3 families. And look at them. They all look like a superworm from the pet store. And then sorting through paper after paper after paper, eventually came upon this paper. And look at this. From just a couple of years ago, a Japanese researcher, look at that larva. And all of a sudden it's like, oh, there it is. So Cano got in touch with Professor Hayashi in Japan, said, do you think this might be Paralichus? And he says, yeah, it's Paralichus. How about that? So there is the living Paralichus up at the top, and here are the type B fossils. And I mean, they're exactly the same size. They're just perfectly, it's so satisfying. And good job, Cano. Really nicely done. Today, Paralichus live, of course, there's lots of them in Japan, but it's got a peculiar distribution. There's actually some in Eastern North America. It's quite rare. There's another species in Eastern North America. There's another species in southern China. There's some in Madagascar, apparently, and there's some obscure record that nobody really understands from somewhere in Latin America. So, what does this mean? Does this mean that, that there were primarily Asian species living in Alberta? Does it mean that now there are Alberta species living in Asia. It doesn't mean either of those things. We have to kind of let go of these notions of where things are native to. They were probably all very widespread during that tropical time, but it's so wonderful. Here's just some photographs from a nature blog in Japan, shallow water. And here's Paralichus. Look at this. It's so wonderful. To us, this is like finding a living coelacanth. This is like the day you wake up and Archaeopteryx is at your bird feeder. And so many of our fossils are like this. And we know that they have to live in shallow water because they actually breathe through this crazy thing off the end of it's. In the literature, it's called a siphon, but really it's a snorkel. You don't breathe through a siphon, you breathe through a snorkel. It's a butt snorkel. And that's how they breathe. So they have to be in water that's shallow enough for this little snorkel to work for these larvae. And they're eating leaf litter, which maybe we can find some signs of what Paralichus eating leaf litter looks like in the fossil record. And we know, again, that there are lots of similar patterns. There are ginkgo fossils in the Paleocene in Alberta. There are ginkgo in Southeast Asia. Now there are metasequoia conifers in the fossil records, and they're now restricted to one part of China. There are fossil mammal teeth that look like dermopterans, the things that are sometimes called colugos or flying lemurs. So we do have this interesting connection that it seems like, as the world went from this wonderful, warm, tropical, not very seasonal time in the Paleocene to what it is now, a lot of things just sort of found their happy place in Southeast Asia that used to be so much more widespread. And here's just one more example. Look at this. This is how hard this can be sometimes. This is a fossil ant. And this is a really good fossil ant. And it turns out that it is part of a group that is now only found. This is from Alberta, again, just from, the place where J.B. Terrell first described the Pascapoo Formation. It's part of a group that is now only found in Sri Lanka. So fascinating. We also have some mysteries. Cano is going to focus on the beetles. And we probably have 30 types of beetles in our fossil collection, we estimate. Only one of them has a name, Donatia whiteni. And Donatia are little reed beetles. They live in reedy places. Here's a modern Donatia. You can find Donatia in Alberta now. This is actually an iNaturalist observation from 2 years ago by Ingolf Askavold, and you'll notice he's also the person who named this fossil back in the 1980s. In his paper, though, he admits that it's not a really typical Donatia. There's some things that make him think, well, this is a weird Donatia, including the fact that it seems to have a color pattern, and all the specimens have that pale margin on the wing covers. So one of the questions is this really Donatia? And why is it so weird if it's Donatia? I don't know. Exciting. Then we have this beetle. I stare at this beetle. This beetle has become my obsession. About every month, I change my mind about what this beetle is. Here's this beetle in inverted ultraviolet fluorescence at 365 nanometers. Does that make it any clearer? No. But it does help you sort of roll new ideas around in your head. And I'm especially interested in, you see that little sort of semi-triangular bit? That's the mesoscutum. And the rest of the beetle is pretty generic looking, but the mesoscutum is potentially useful for identification. And what's in the inset, there's the mesoscutum that I dissected out of a beetle from China that I think might be related. A trout, or not, what do they call it? Forest stream beetle, a eulicatid beetle. This is what eulicatids look like. Is that what it is? I don't know. So far, it's looking pretty good, but we're having so much fun trying to work out these mysteries. The one that is still most mystery, and I'll finish with this particular beetle. That wing cover is 35 millimeters long. So the whole beetle was probably like 45 millimeters long. That's a big beetle. The average size of a beetle is about 3 millimeters. So this thing, at any period in Earth history, this was way out on the one end of the graph of, size of beetles. So we should be able to figure out what it is, but we don't know. And one of the open questions here is that we've got 3 or 4 of these from the Paleocene, but there's a very similar beetle from the Eocene, so 10 million years later, 10 million years closer to us in time, from British Columbia, from Driftwood Canyon. And Mark Wilson published a photograph of this way back in the 80s. It's been in the public eye for decades, and nobody has ever been able to figure out what this beetle is. I think they're the same thing, and so they survived, at least from the Paleocene to the Eocene. But they don't look like any living beetle to me, and I think it's just a wonderful mystery. So there's lots to be done, and we're in wonderful company as well. When Cano started on this, we kind of thought that she was alone, and then we've had great collaborations with Corentin from Oxford. Ryusuke Kimitsuke is a PhD student doing trace fossil work, ichnology at the U of A, and we've worked with him on some interesting trace fossils that we found in the course of our work. Christine Sosiak, she's here with us today. She's a postdoc with both the Terrell Museum with Dr. Christopher West and the U of A, working on big, broad patterns of insect-plant interaction. So we're all kind of feeling like we're part of a renaissance of the study of these insect fossils from the Paleocene, which is really exciting. Now, when I was putting this talk together, the last thing I did was read the abstract that I sent to the museum a long time ago, and I realized, oh man, I forgot to say something, because I was supposed to tell you about the beetle's perspective on the Paleocene. And I think that the beetle's perspective is that, if you were a beetle in the Paleocene and you went through your average day, that day would be an awful lot like the relatives of those beetles living today, even if they don't live here. It's just amazing how much the beetles have not changed that much, at least the beetles from these fossils. It's like the more things change, the more they stay the same. The only thing that's really new is that some species of beetles managed to stay here as this place became so much more seasonal. They have ways of dealing with winter. Alberta winter is something really new for the Paleocene crowd. But for the most part, it's just this wonder. Almost all the fossils we look at, are now living fossils. Like, we can look at the fossil and then we can go out and look at the living beetle. And you watch these beetles and you go, well, you've been doing that same thing that your ancestors did countless millions of times. I love that. I love part of the story of life is this story of progress and diversity but part of the story is just stubborn doing the same thing because it still works. And I don't know, the older I get, the more I like that. All right, and I'll finish with a picture of Cano. This whole story will undoubtedly change over the next couple of years as she finishes her master's work, so stay tuned. But in the meantime, I'm happy to have the chance to tell you about it, and I would be equally happy to answer any questions. Thank you for your attention.
Hi. I was just wondering, because many macrobenthic invertebrates today are used as indicators of habitat health, particularly in aquatic ecosystems. Do we know if that can be applied to the fossil record as well?
Yeah, that's a really interesting question, and I think, and you're right. There's a lot of that kind of work going on. Most of it, like in Canada, we have this thing called the cabin protocols and so on that feature into that. Most of that work has to do with the health, and remember, health here is a metaphor, right? With the health of flowing water ecosystems. And it also has a lot to do with the health described as what is good for fisheries. So the ecosystems in which our fossils were laid down were generally without fish. At least we don't find the fish fossils in the same strata as the insect fossils. and they were not flowing, at least they were only intermittently flowing enough to lay down some sediment. They're just exactly the kind of environments where no agency would bother to check for ecosystem health with indicators. So we can't take those protocols and apply them to the record directly. That might be possible if you had a good situation where you had flowing water laying down your fossils, but we just don't have that kind of thing in Alberta. But good question, thank you. Okay, the question is whether there is any fossil evidence of insect predation, in the stomachs of other fossils. Well, I'd say so far we have none of that, but remember please that it's so exciting when you have like a fossil fish or a mosasaur with a skeleton inside the body cavity, because that's how a lot of these vertebrate predators, that's how they eat. They just grab their prey and they swallow it whole, and there you go. The insect predators that we have in our fossil record, things like the giant water bug. Well, how does the giant water bug dispatch its prey? It injects it with a digestive enzyme, liquefies the prey, and then sucks up the liquid. So you're not going to get anything in the stomach contents from a predator. How do ground beetles do it? They chew it up. Again, they're called extraoral digesters. It's a very disgusting concept. And then they digest it in a bolus of digestive enzymes that they roll around in their weird fingery mouth parts. And then again, they take in the liquid. So you're just not expecting that kind of preservation in the fossils. It'd be cool if we found it, or if, it'd be nice to find like some bug stuck in a fossil spider web. That'd be cool. But we just haven't found it. Yeah. But thanks for the question.
Talking about some of the philosophy of biology ideas you were talking about, like, I don't know, structures or animals, I guess, being slow processes, or to what extent species are a thing or not. Is that something you apply practically to the work you do, or is it something that like knocks your socks off and then you put your socks back on and go look at some beetles or something like that?
No, good question, Ian. And sorry about the cough. Let me take a little chance here and say that, when you're doing descriptive paleontology, taxonomy, probably not. But if part of the job is communicating the story of life to a broader audience, then I think we really do have to take those philosophical considerations, to heart, and think very carefully about the language we use to convey these stories. Because, I don't know, at least for me, it's more important to get it right than it is to tell people what they expect to be told, if you know what I'm saying. Does that make sense?
That does make sense. Can I ask you a follow-up?
Sure, please. Yeah.
Given that we're using these metaphors that we don't think are metaphors necessarily, do you think, based on these other ideas you're talking about, does that maybe, because we're not recognizing them as metaphors, does that constrain our thinking or send our thinking in wrong directions, like in a practical way, that we might be discovering truths that we're not discovering because we're thinking about them with incorrect metaphors?
Yeah, good question. And I'm not dodging the question, but I'll tell you that I've thought about this also in the context of, the other parts of my career in conservation biology. And I think when we start applying superorganism metaphors to ecosystem management, we can make strange mistakes as conservation biologists. So I think it's the practical repercussions of the metaphors are more obvious to me in the modern world, and how we manage places like parks and protected areas, and I'll think about that though. I should have had a good answer ready for that question. Good question, Lee. Yeah.
Thank you.
The question is, does there seem to be any preservation biases against any particular elements for insect fossils? I think the answer is for sure yes. For the beetles, for example, we basically don't find beetles with legs and antennae, which is super frustrating because how do you identify living beetles? Legs and antennae. We just find the body. And it's probably the case, if it's a situation like the situation that's been looked at more carefully in BC in the Eocene deposits, probably you had dead insects kind of floating on the surface of this still water body and slowly decomposing, and the leg falls off here and the other leg falls off there. And eventually you get whatever's left being preserved in the fossil record. So yeah, there is certainly a bias, and with beetles, it's wing covers, the elytra that are most common. With cockroaches, it's almost always the forewing, the tegmina, that's most common. Yeah, so there's certainly a bias toward particular elements, and the preservation is astonishing. But there was also clearly some decomposition before these things were fossilized for most of them.
John, is there any Paleocene amber that preserves insects that might be helpful in any of this?
Well, if there is, it's possible. It's all kind of small bits of really crumbly amber that we've seen so far. So it's not impossible, but we don't have any insect-bearing amber yet from the Paleocene. But good question, Andy. Yeah.
I'm interested in the comments you made about the category versus metaphor. How are you finding associations between your fossil and what's already in the record and being analyzed? Because this kind of reminds me of Michael Healy that worked for Boeing Aerospace in Seattle, but also was a university prof and eventually ended up at University of Arizona. He was really fanatical on the category. He loved category theory in mathematics, which is maybe a different thing altogether. But one of the key things was how to actually not recognize parts in Boeing, but recognize parts from older parts in Boeing that had been used in aircraft, because it was a huge issue not to design a new piece, which was so expensive, the whole thing. But if you had a piece that had not just anatomical resemblance, but functional resemblance that could fit your needs. So they had to use category theory in mathematics with neural networks to be able to kind of build a specialized database for recognizing pieces. Do you do the same thing in paleontology in general? Like if you have a fossil, it's not that there's a right answer or wrong answer. It's that there's 100,000 pieces that could be what you're really looking for. So it's not to have a database that has, you put in the characteristics and there's the answer. It's more like you put in the characteristics and there's 100,000 answers to analyze.
I think that's kind of an emerging field, but I'll just, to take the analogy with airplane parts, it is very likely that the fossils I've showed you have been recognizably bug-like, right? And I did focus in on that one structure in the fossil beetle, the mesoscutum. We are probably looking at all sorts of little bug body parts in these fossils that we're not recognizing as such. It's just like a little speck in the rock here and a speck in the rock there, and we're just looking for something that resonates with us. And that is exactly the sort of level of detail that we're probably missing. And we're also missing all these trace fossils, tracks and little slide marks and stuff. That's the sort of thing that I think machine learning is going to be very good at overcoming human perceptual bias and allowing us to explore that area. Yeah.
I get feel and not being any expert in the modern AI, but that's precisely what things in neural networks are doing for well over 20 or 30 years.
Yeah.
The new AI is probably just a lot easier to use, to self-evolve and develop on the data set. Not even.
Yeah. Oh yeah. No, you're so right. And even with, I can go out and I'm sure many of you have done this. I can take a picture of a living insect on my phone. I can upload it to iNaturalist. It goes through an AI process. It says, oh, it's Donatia. It's that reed beetle. I can't take a picture of the fossil and get it to do that because it only recognizes images of living beetles. It doesn't recognize, there's no database that it's learned from of fossil images. So it's really too bad that the AI can't translate from the living realm to the fossil realm or backwards, but so far it can't. All right.
Alrighty.
Okay.
Well, thank you, John.